Okay, so perfect. Today's first session, we are going to deal with a few things, which I told you. First, we look at basics. I mean, basics of literally the basic of SOM, right? So, first off, I'll have a bit of apologies that session took too long, and the other thing, I'm going to use my mouse. So whatever I'm saying, you just have to write it. Okay, because when I write over here on the laptop using a mouse, I don't have that stylus right now. My stylus is broken. So if I write something like this, I have written body, so I'll dictate also. You just have to keep writing with me. Okay, so just bear with me. So we'll start with basic of SOM. So at the very basic of SOM, there are different types of bodies. How many types of bodies do we have? I'll give an example. First, we have a rigid body. Yes or no? Rigid. And then we have deformable body. Am I right or not?
Yes, sir.
Okay, just keep writing with me. Keep write down. Keep writing it so that you understand what I'm trying to say. Now, within deformable, how many types of deformable bodies do you think you will have? Can a solid be said as deformable solid? And can I say that fluid is also deformable? Yes or no? Yes or no, guys?
Yes, sir.
Yeah. And amongst solid, there are two types of analysis. Two types of solid deformable bodies are there. First is static, where the entire system is stable, it's not moving. That static load, no motion, zero velocity, everything. And the other is a dynamic body. All right. And the other is a dynamic body. This study, this is called SOM, strength of a material, or mechanics of solid, or let's say this is called as solid mechanics. Okay, what you are going to study is called as solid mechanics. This is solid mechanics. So a, a body which is deformable, which is solid, and it is static in system is the study of solid mechanics. Okay, you understood everybody till here, right?
Yes, sir.
This is the utmost basic level what I'm trying to tell you. Okay, perfect. So you understood what is solid mechanics, or basically strength of material. Strength of material is a study of static, solid, deformable bodies. Static, solid, deformable bodies. Right. Now, how do you say? When do you say a body is rigid? When do you say a body is rigid? Somebody tell me. Let's say this is a body I'm making. I just made some, let's say a rectangle. When do you say that this rectangle is a rigid body? When the dimension at any point inside the body will remain same at any amount of load, correct?
Yes, sir.
This is a rigid body जहाँ पे dimension at any given point of load will be same, will be constant. It's a rigid body, and rigid in this world, there is nothing rigid. There is nothing rigid in this world. Everything rigid is an ideal condition of a body. Now when you say that, okay, let's imagine this is a wall of a building, or the wall of your room. ये तुम्हारे घर की दीवार है. Okay, and you say that you are trying to push it and you're not able to push it. So do you think this is rigid? No, no, this is not rigid. This is not rigid. This is rigid for the amount of force it is experiencing right now. The force, let's say it is only experiencing about 100 newton. But what if I bring a big, wrecking ball and just shove it over here, and its force is almost 10 to the power 8 newtons? Will it break or not? It will break, no? Yes or no?
Yes, sir.
So you can say that this wall is rigid for a certain threshold of force, but not for all forces. This wall will not be rigid. So the definition of rigid in real life depends upon what kind of situation or is your system being exploited too. Okay, so there is something called as a rigid body. Then you have something called as deformable body. When do you say a body is deformable? When you apply a load P, and what happens? The body deforms. Yes or no? Is it a deformable body?
Yes.
Yes, this is a deformable body. That's what you say a deformable body. But let's say that this P load has some kind of threshold. Let's say I will say that P deform. At a given P, it will deform. But for any value of load which is less than the deformable load, will it deform or not? It will not deform, right? Right?
Yes.
So for every load which is less than the deformable load, the body will not deform. Such a property of a body is called being resistant. Okay, do you see? It's called a resistant body. Resistant body means a body that shows rigid behavior up to a certain amount of external load is a resistant body. Like वो wall को जब तुम push कर रहे थे, when you were pushing the wall, it was not moving. That means the wall was showing a resistant behavior towards your applied load. But अगर wrecking ball आता है पीछे से crane के साथ, तो वहां पे वो टूट जाएगा. That means the wall will not be able to show its resistant behavior. Everybody understood? Jaswant, Bhavishri and everybody.
Yes, sir.
Yes, sir.
Okay, perfect. So this is called a resistant. This is the virtue of a, it's a property. Not a property, but it's anything. Let's say it's about you. All right, you end up in a fight. All right, it is said that if you get in a fight, you can only handle at least, let's say, three punches. The fourth punch is going to knock you out. So what does it say? That these three punches are your resistance. At least you will be able to handle three punches. All right, let's say there's someone even stronger, he can handle 13 punches. So this thing is resistance of his, it's his characteristic, it's his property that he can resist that much. 14th punch will knock him out. All right, plus one and he is a knockout. That's it, done. So now you understand there's something called a resistant body. Okay, so we'll move a bit ahead and we'll define what is SOM. Okay, now this is something important which is asked in interviews and sometimes was asked in gate. Okay, wait a minute, I'll just change the color also. No worries. Okay, SOM is the study of internal resistance forces developed during elastic deformation of a body under external loads. Okay, let's understand this sentence very nicely first. Okay, what I'm trying to say. The first part is that SOM, the strength of materials. This subject is what? This subject is study of internal resisting forces. Study is the study of internal resisting forces. Alright, this is an internally resisting forces. What? During the elastic deformation. Just go through all the keywords which I'm trying to tell you. Okay, first, this SOM is an internal resisting forces during the elastic deformation under external loads. Okay, so if this is your body and let's say it is fixed at some end. Acha, you know that you are applying a load over here, P, correct? Then what is this P? You did not apply this P. ये P क्या है? What is this P? How, where did it come from? Where did this P come from? It was fixed. You cannot apply a load over here. Physically, it is not possible because this part is fixed. You only
Reactive
applied a
force.
load here. What is this?
Reactive force.
Exactly. This is reacting force. This is the internal resistance. Alright, this is the internal resistance because by the virtue of physics, a basic physics क्या कहता है? A basic physics says, a Newton's law, if you go to Newton's law, it says if a body is in rest, just remember this, static. If a body is in rest, it will always have a tendency to restore itself to a condition where it remains in rest. Inertia कहते हैं उसे, right? Yes or no?
Yes, sir.
Second law of Newton. Body में inertia आती है. If the body has is already in rest, yeah, it is already in a motion of constant velocity, it will, any kind of disturbance, the body's own physical dynamic will return itself to its original position or its original state, है ना? So you apply
Yes, sir.
this load P, and by basic physics you see that internally एक resistant force induced हुआ है. So your strength of material will be the study of internal resisting force during elastic deformation. ये क्या होता है? We'll study more about when I'm doing Hooke's law थोड़ी देर में, just a bit of the under external loads. I have an external load also. So this is your SOM. Okay. Now why I say elastic deformation? Let's look at that. Okay. Now what do you mean by elastic deformation? Elastic deformation. Okay. So if you look at elastic deformation, what do you see? First off, let's say there is a bridge. Okay, I'm drawing a simply supported beam, but let's assume this is a bridge, or you can even assume it as a beam, whatever you say. There are two types of bridges. One bridge, the material of one bridge is in elastic region, and while the material of the other bridge is in plastic region. Okay, let's say this material is in elastic region, and the material of this bridge is in plastic region. Okay, and if you try to put a load, let's say तुमने यहाँ पे load डाला, you put some kind of load, and you put the same load over here. Let's say I put 100 newtons, and here also I have put 100 newtons. Okay, I put the same load at both places. Now what happens? I see that this bridge goes here. Okay, and this bridge also goes here. Let's say deflection is same in both the cases. The deflection of the beam is same. And here also it is delta, and here also it is delta. But what happens when you remove this load? When you remove this load, what do you see? That the bridge returns back to its original place. And when you remove this load, you see that the bridge does not return to its original place. Tell me, which one will you prefer? Which bridge will you prefer in making the bridge? Obviously the first one, which is an elastic deformation, right? इंटरव्यू में बहुत इंपॉर्टेंट एक क्वेश्चन आता है. You know this answer to this? Okay, if you YouTube, or if you Google this this question, you will get the answer. Okay, that is your homework. You will 100% get the answer to this question, which is more elastic, steel or rubber. But now I am giving you a homework. Find out what is the meaning of elastic in this context. ठीक है? What is the meaning of elastic over here? We all know that steel is more elastic than rubber. We also know the reason, because there's something called as Young's modulus, and steel remains in the plastic region, in the elastic region below yield strength, and there is no fracture point after that. We all know that, the physics of Hooke's law. But now I want you to understand what is the meaning of elastic in this context. Then you will understand what do you mean by elastic deformation. Okay, so this is the homework which I'm trying to give you. Okay, what do you mean by elastic in that context? All right, so now I'll be moving ahead. Why do you need elastic deformation? Few points. First, it is recoverable. All right, any kind of deformation you do will be recoverable over there. Second, you do not want plastic. I don't want plastic. In plastic, the deflection is large. Okay, and plastic is non-recoverable. That means वो वापस अपने same size पे नहीं आता. That is why you prefer elastic deformation in strength of materials rather than plastic. Your entire SOM study, your entire subject of SOM will range in this area. You are never going to study plastic deformation ever. Okay, this is what it is. Now let's go to somewhere which is called assumptions. And here I will be very strict. You have to pay attention because I'm going to tell you something very important. Okay, now you'll have something very important. First, I'll just write it down for you. Assumptions in SOM. If you have seen the playlist which I'm sharing you, you would have studied it. But if you're not, then pay attention over here. I'll cover everything over here. All right, no worries. Okay. So first point is, let's say components, massless. Don't worry, I'll explain every point to you. Materials should be homogeneous and isotropic. All right. So we see that there are, a bit of so many things that have just come up in front of you. All right. So I'll ask you, see, do me a favor. Let's start from very basic. Okay. First, we'll pick up this that components are made massless. Okay. Can anybody tell me? Now I want to ask questions. Okay. Bhavyashree, why do you think components are made massless? No worries. Galat bolo. I don't care. Give me a wrong answer also, but I need an answer.
Yeah, so, like, as we are concentrating only on the application of load, like, the mass is not considered.
Perfect. Correct answer. Then, Jashwant, do you have anything to add?
No, sir.
Okay, cool. So, see, masses components are made massless. That means, let's see, if you are analyzing, let's say this is a hook and you are analyzing a fan. Fan will have three blades. Okay, you have three blades, but finally, what is this is let's say this is a circular part, and these are all blades, and this is the hook. Now, if I ask you what is the load on fan. This entire thing is a fan. Okay, a fan has three components: hook, blades, and circular part. What is the load on a fan? Fan पे क्या load हो रहा होगा? What is the load of a fan? If you didn't understand, let's do it in this way. Tell me the load on hook. What will be the load on hook?
Weight of fan.
Nope. Will it be weight of the circular part plus weight of blades? Yes or no? Yes or no?
Yes, sir.
Plus the weight of rod, right? This rod. Alright. So you see over here, load on a hook is the sum of everything, but a fan as an entire unit, its load will be zero. Why? Because do you exert force on yourself? If I say what is the load on legs of a man, let's say the weight of the man is 80 kgs. So what is the load on the legs? The legs will have 80 kgs. Okay, but what is the load on this entire man? Zero. कोई बॉडी अपने ऊपर खुद से लोड नहीं लगा सकती है. Yes or no?
Yes.
You need an external factor, right?
Yes.
So now you see the concept of being massless. This is called being massless. Okay, a body cannot exert a force or a load on itself. That is why we see that the components are made to be massless. That is what you consider. All right. Next is materials to be made homogeneous and isotropic. Now this is an important point, and many people are going to make mistake over here. First, let me ask you. Yeah, Pratik, are you there?
Yes, sir.
Okay. Tell me, what do you mean by homogeneous material? First, we'll focus on this word. What do you mean by homogeneous?
Like same composition, like
And okay, same composition, that is a chemical definition. I want a mechanical, a material definition. Homogeneous is a property. So I want a material, a mechanical definition, not a chemical definition about composition and quantity. Tell me, try.
not kind of an alloy or something like that.
Okay, that is still a chemical composition. Bhavish, you want to try? What is the meaning of homogeneous material?
So like different points, same direction, elastic property will be same.
Okay, no, correct. See, it is that exact thing. A material is said to be homogeneous when it shows same elastic properties at any point in a given direction. Okay, so let's say if I'm choosing this direction, the property in this direction will be E1 at every point. All right, okay. But now if I change the direction, the property also changes. Do you get it, guys?
Yeah.
The property now in the other direction is different. Let's say E2. Okay, you choose a different direction. Let's say this direction, it is E3. This direction, it is E3. So if you change the direction, the property will be different, and that property will be same at every point given the direction is same. All right, so this kind of material is called homogeneous. Alright, Jaswant, what is isotropic material?
Sir, having same properties throughout, sir.
Same properties throughout. Are you sure?
Mm, yes,
Like
sir.
uh, having the same properties at means for a particular point at a different directions, the properties will be the same.
Yes. That if you choose any point, let's say this is point 1. So at this point, the properties will be same in every direction. Correct. This is correct. Understood. Now when you change the point, the properties will also change, but they will be same in every direction. Now do you understand the meaning of isotropic?
Yes, sir.
Yes or no?
Yes, sir.
This is not my definition. This is the definition in the book James M. Gere. And a lot of people get confused. Alright, this is isotropic. Now if you move homogeneous plus isotropic, you will have same properties at every point in every direction. E, here also E, here also E. So this is the material that we use for study of SOM. Now do you understand what is the meaning of homogeneous plus isotropic? Write it down somewhere or maybe draw this figure. Okay, so you should be knowing this. First, what do you mean by homogeneous? Homogeneous means same properties at any point. At any point, but in the same direction. But in same direction. This is also called same on all locations. Same on all locations. This is called homogeneous. Okay, I'll write it here. This is homogeneous. And the definition of isotropic, I'll edit isotropic. It says same in all directions. Okay, this is the definition of isotropic. Isotropic means same in all directions. So you have to first understand the first things. First we knew, now we know what is the meaning of massless. Now we know what is homogeneous isotropic. Now it is prismatic. What is the meaning of prismatic bar? What is the meaning of prismatic bar? Ice prismatic bar.
Like the cross section should be uniform.
Uniform with
Uniform, along the axial direction.
perfect. If you have an object, prismatic means that your cross section should be constant. It should not vary. The cross section should be constant throughout. That if this is the cross section, this cross section if this is the direction x, let's say this is x direction, your cross section a of x should not vary. It should be constant. The cross section should be a naught. Can I say that this function clearly says that a bar is prismatic? Yes or no?
Yes.
Yes or no?
Yes, sir.
Yes.
Okay, perfect. So now you understood that I say if let's say if this direction is x, then an equation for a prismatic bar will be that your area along x direction will be constant. This is called a prismatic bar. Perfect. Now what is why now tell me what is the meaning of engineering stress?
Sir, I haven't got it.
What Bhavishri, you're not audible.
Sir, in SOM, why we will consider a prismatic bar only, sir? Like,
Okay, see. Now there is a condition. There is also a case where you don't use a prismatic bar, where analysis is a bit different. Okay, if you have there are obviously a variation. There are different analysis to this. If you see for massless, there is a case where you do elongation, self elongation in a bar due to its own weight. Right or not?
yes, sir.
You have self elongation because of its own weight. Perfect. Now let's say you have something non-prismatic bar. Let's say I have a tapered bar. Okay, this is a tapered bar. Why do we do use a prismatic bar? Tapered bar, let's say its tapered bar is also very uniformly tapered. There is a very linear relation. Let's say you have a bar like this. This is the first cross section, and then it goes like this. If this is your bar, if this is your cross section where of the bar, tell me how honestly you will get a very accurate result. Let's say you fix the same bar from here and you try to give it a moment. The first thing it will break from here. Yes or no?
Yes, sir.
Yes.
Let's say if you give a upper moment, it will break from here. Let's say if you try to give compression, the bar will always break from a point where there is minimum area, or it will always buckle at a point where there is a great point of inflection. Yes or no?
Yes,
That is why you have to use a prismatic bar so that at least you know that your analysis will be running throughout uniformly. Okay.
okay, sir.
Other thing, let's see about self weight. If you let's say I'm dealing with cantilever. All right. Yeah. Let's say right now I have a prismatic bar, but it is not massless. It has some kind of a mass. Okay. This I have fixed it here, and I am going to make a cantilever beam out of it. Okay. But I see that this has a weight. Weight is in x direction. Let's say it is something w naught of x to the power minus 1 by 3. Okay, let's say plus 1 by 3. Let's say weight is varying somehow. Alright, it is not uniformly distributed. That means the component is not massless. I have considered two different things, massless and non-uniformity in distribution. What is going to happen? Will it going to shrink like this? Will it shrink or not? It will shrink, right? Or not?
Yes, sir.
Tell
Will.
me which one will you rely? Applying an actual load over here or applying an actual load over here? If you apply an actual load over here, this entire thing is going to bend. If you apply an actual load over here, there will be a small amount of, even the smallest amount of compression over here, right? Yes or no?
Yes, sir.
Yes.
Yes, sir.
When you want to compress and test, you will not do this. You will want to have an ideal condition. Since in real life nothing is massless, so what do? You vary this load such that it becomes only compressive and not momentous. Alright. But now you tell me, what do you mean by engineering stress? What do you mean by engineering stress?
When we plot the stress strain diagram, then while calculating, we take the original area of the cross section. We don't take the changing area of the cross section.
Very true, perfect. That's a nice answer. Engineering stress is basically, let's say, sigma engineering. And what is true stress? Same, Pradeep.
When we take the variable cross section.
Variable. Yup. This is the original ORG. If you are writing down ORG, original. And then let's say there is a true stress. True stress is nothing but your applied load divided by the instantaneous area, that area at that point. Okay, that is your true stress. True stress is basically used when you have to, manufacture something. That means at the time of when you have to determine failures or manufacturing loads. So true stress is basically used at manufacturing level. All right, or you use it during failure analysis. Most of the time you will always consider original area because you do not know at what rate and what is the different area at different instants of time. So that is why you only use engineering stress and engineering strain. Okay, so this is the definition for engineering stress and engineering strain. Now your material should follow Hooke's law. This is important. It should follow Hooke's law and Saint-Vincent's principle is valid. First we see what is Hooke's law. Hooke's law, you all know that stress should be directly proportional to strain upon until elastic limit. Till elastic limit, stress is proportional to strain and the slope is equal to Young's modulus. Slope, which is sigma by E epsilon, is Young's modulus. If it does not follow Hooke's law, that means it is simply in the plastic nature or it is somewhere at the fracture, that then it becomes the same thing. It becomes the same thing that you are neglecting this part where it has elastic deformation. This, you are neglecting this definition. To maintain this definition of elastic deformation study, you have to maintain a Hooke's law. Okay. Now I'll tell you what is Saint-Venant principle. Okay. Saint-Venant principle is simply, and I'll write it down, you'll understand it yourself. Saint-Venant principle is maximum stress will be developed near the application of load. So do you understand? Do you have any doubts in Saint-Venant principle? Tell me if you have doubts. If you did not understand how is this happening. Does anyone have doubts? Okay, let's see an image. You'll understand very easily. You see Saint-Venant principle. Now I'll show you an image. What happens? Um, okay. Do you see this photo?
Yes.
All right. Everybody sees this photo. All right. In this photo, just see one thing. Your force is applied over here, and see every kind of stress lines are converging to the force. But as you go beyond, the stress lines is same. That is what I meant by saying that maximum stress will be developed near the application of load. Now you understood,
Yes.
right? In any kind of dimension, it is going to be possible. Okay, that your every load is happening near the application of load. Every maximum stress will occur near the application of load. That is your strength balance principle, and this is what your assumptions in SOM. Okay, now let's go with Hooke's law. Okay. Okay, tell me how many of you know Hooke's law completely? Guys, anybody? Hooke's law. Tell me the diagram of a Hooke's law. How will you draw? Okay, help me with this. Yeah. I'll explain you Hooke's law very nicely. Just write down what I'm trying to tell you, and you will understand every bit of it. Okay.
Yes.
Let's go to Hooke's law. Wait, let me open my notes of Hooke's law. So in Hooke's law, you have basically entire region is divided into three parts: elastic, plastic, and the plastic deformation region. And beyond that, it is a fracture point. Okay. So draw this between. This is your stress, and this is your strain. First curve. Then you have a bit of a turn. Where to the different pencil? Yeah, bit of a turn, and then okay. Draw it with me. Right. Then is your final curve. F E D C2 C1 B A, and this is O. This is the region between B and C1. Okay. This is yellow colored region. Bear with me and I'll explain you Hooke's law very nicely. Okay. Then you have this region which is entirely blue color. A to this is O to B. Okay. This entire region is blue colored. Then there's this region O to A. Alright. First copy this diagram till here and I'm going to tell you what happens next. This region is a plastic region. This is the plastic region, okay? This entire is the plastic region. First draw till here and I'll be back in a minute. Yeah, hi guys. Pradeep, Jaswant, Abhishek. Have you all drawn this?
Yes, sir.
Okay. So just remember, keep this page open, and on your next page, start writing what I am writing. Okay, and you'll understand everything. First is that point A. A is called proportional limit. B is called elastic limit. C1 is called upper C1, C2 both. Upper and lower limit. Yield point. Lower limit of yield points. D का कोई नाम नहीं होता. There is no name for D. Okay. E is a because most of the books have this notation of D, but still they don't mention it. F is failure or fracture. Okay, and just use this over here in this page itself. F is kept here. Yeah, okay, perfect. A, B, C, D, and F. All right. So first you see till point A is your proportional limit. That means your stress and strain are proportional to each other, and the Young's modulus is their slope. From A to B is an elastic limit. That means if you move beyond A till A to E, there is no problem. Your stress strain will be there, and the moment you remove the stress, there is no strain. Beyond this is elastic limit. Till here you can at least extend, and the entire system will recover back itself. After B and C, these are yield points. Over here, your elastic limit starts to yield and turn into a plastic state. Okay, from D, E, and F. This entire is a fracture or burn area where your subject again starts stretching. Here is the point where you start getting your necking. Okay, if you have done tensile testing of a simple bar, your bar would be very straight. Okay, first it will go through a yield strength, and then at point D, somewhere near point D between C2 and D, it will start to increase further. It will start to have zero strain but increase in stress. The strain starts to remain here only. This is the point where the strain remains like this. All right, strain is increasing at the same stress. This region C and D, the strain is increasing but the stress remains the same. Let's write it sigma C2. This is a very crucial point where after this you always know that it is going to fracture. So this is the part where it starts to have neck formation. Do you remember neck formation from your workshops in BTech? Necking of the material? Guys, do you remember?
Yes, sir.
Yeah. So at that point it gets into necking, and then there is ultimate stress, and then there is fracture. At fracture you have a cup and cone shape if you are testing a stainless steel. Okay. Now we are going to do is we are going to analyze each and every point until we reach something called as strain energy. Okay, so let's go back. OA is the proportional limit only region. This OA. Write something about OA. If you write OA is proportional limit, this is the only region Hooke's law is valid. So your entire SOM will range in this region OA, ideally. Okay. A to B is a non-linear. Remember this word. It's a non-linear region. Don't confuse it ki A to B. The region is going to be linear. Okay. Then you have the region AB is coincides. Say Hooke's law is valid till elasticness. If Why do you say that Hooke's law is valid till elastic limit? Because A and B coincide in some cases. Okay. Now you're talking about region OB. OB is the region which is the elastic region. Elastic region materials exhibit elastic behavior. Elastic means if you stretch them, they will come back to its original shape. That means they are called recoverable shape. Okay. Okay. Now there is something very important which you have to understand. I'll write it over here. Right. You won't get this anywhere except the playlist which I sent. So I'm just kind of revising the playlist for you. Solids are. Let me first write it. Okay, what do you mean by this sentence? Anyone? Bhavyashree, Jaswant or Pradeep? What do you mean by this? What do you mean by this sentence? Solids are perfect memory substances. What do you mean?
It doesn't deform much.
What?
It doesn't undergo deformation.
अच्छा, how can you say that? Stainless steel को अगर तुम pull करोगे तो it will deform. So it will deform. What do you mean by perfect memory substances? Pradeep, Jashwant.
Sir, fluids fluids flow in any direction, no, sir. Like
So
they follow
okay, I'll tell you. See, it is a way of saying that they are elastic. Okay, it is simply a way of saying. I'll just write it here. Elasticity is nothing but memory of a substance. Acha, tell me if you say that the size of the steel bar under elastic deformation. I'm trying to deform it elastically. Let's say it expands to this much. Let's say that this elastic expands a bit. Okay. If you know that this elastic has expanded a bit on the use of this load P, and if you remove this load P, what will happen? Will it go back under elastic deformation? Yes or no? Guys, be fast. Will it go back in elastic deformation? Yes or no?
Yes, sir.
Yes or no?
Yes, sir.
Yes, exactly. But have you ever seen अगर मैंने steel को pull किया है and the moment I remove this force, what do you see? It will go back to this position, no? Or will it become something like this? It will go back to exact same position, right or not?
Yes, sir.
So this is why it is called a perfect memory. It has a memory of its own. इस डिफॉर्मेशन की इस पूरे मटेरियल की एक याददाश्त है. It has a memory कि इसे जाना है same route पे. It has to recover itself in the same shape and size it was deformed to. Okay,
Okay,
that is
sir.
why it is called a perfect memory substance. Let's say a drop of water. A drop of water is falling down. All right. You right now you know the shape of this drop of water. Okay. The water droplet, it has a shape right now. You know this shape is due to what? Surface tension. Surface tension is also nothing but it is what? A force. And if it is per unit area, it is a stress. Now you see this is a ground over here. Now this is going to hit the ground. That means there is something called as impact loading. Have you studied impact loading or do you remember the name? Yes or no?
Yes, sir.
So let's assume that this surface tension, if this entire droplet hits here, it happens in impact loading and it deforms. What is the guarantee? Do you have a guarantee that if it deforms, it will come back to this same exact shape? Yes or no? No, right? Right or not?
Yes, sir.
If this is a water balloon, if you put a needle over here, if you pierce it with a needle, will it remain the same shape? Will the water inside it remain in the same shape or not?
No, sir.
Exactly, that is why it is called that fluids are zero memory substances. If you deform them, if you displace them, they do not have anything that can make them come back to its original state. Yes or no? Yes or no, guys?
Yes, sir.
So write this down. Solids are perfect memory substances while fluids are zero. Elasticity is also called as a memory of a substance. Elasticity is nothing but memory of a substance. This is important for you all to understand. Okay. Now what are perfectly elastic material? What do you mean by perfectly elastic materials? Guys, okay, I'll tell you. A material which follows, sorry, which satisfies following three conditions after removal of the load. Okay. Condition number one, complete recovery of dimension. Now, since you did not answer me what is plastic perfectly elastic, you will answer me the meaning of these conditions. The recovery should be instantaneous. Follow the same path. Okay, Pradeep, let's start with you. What do you mean by perfectly elastic? Did you understand the line? What is a perfectly elastic material? Pradeep, are you there? Or is not there? Okay, just one.
Yes, sir.
Okay, tell me the meaning of the first thing. Complete recovery of dimension.
So the dimensions should be the same after it comes to the original position and after applying the after removing that load, sir.
Correct.
It should
Perfect.
be
Now, what is the meaning of recovery? Should be instantaneous.
sir. It should be instantaneous. After removing the load, sir, it should be instantaneous. Like it should come back to its original position.
Exactly. Perfect. It should not take a long time. As the moment you remove the load, the moment it should be back to its position, right?
Yes, sir.
Yes. And follow the same path. That means I'll tell you the meaning to
Uh,
this. Let's say you have a scale, a steel scale, 30 centimeter का steel scale आता है. Let's say you have a scale. Okay. You pull the scale from both ends. You put the scale inside a universal testing machine. You pull the scale, and the moment you remove the load, Let's say the scale completely recovers its dimension. It also recovers instantaneously, but it comes like this, and then it becomes straight. First, it starts to wobble, and then it becomes straight later on. So it does not follow the same path. Yes or no? The scale was straight. It elongated in a straight direction, but while recovering, it first wobbled like this, and then it recovered. So do you say it followed the same path? No, right?
Yes. No, sir.
So this is the meaning of following the same path. Okay. Now I'll define this to you in a nice graphical manner, and you'll understand it very easily. Okay. Let's say that this is the curve, stress versus strain curve. All right. This is point A, and only till proportional limit. I am going till A. Now, if I go till A in this path, that means my if I'm applying stress and strain is also applying, I'm going in this path. But for it to be perfectly instantaneous, let's say this is one curve it follows, this is B, OB, and this is the other curve it follows, OC. Sorry, not OC. Uh, the curve is this. Okay, first let's say this entire thing comes back to zero by curve B, and this is another curve, this goes OC. Okay, and this is first curve returned by the first same line. Tell me which curve represents a perfectly elastic material.
Oh,
OA, yes, exactly. OA is a perfectly elastic. Why? In case of this material, this curve, B curve, what happens in B curve? First point is it goes to zero. That means it recovers the dimension correctly. Instantaneous is a doubt because there is, this is the area under consideration. That means it has taken a longer time. Yes or no? Yes or no?
yes, sir.
So instantaneous it does not satisfy. Next, it does not follow the same path. Okay, this is for case of B. What happens in case of A to C? What happens? It does not recover completely. There is a residue, right?
Bro, net
Instantaneous is not
వస్తుందా?
there. What happened? Okay. So
వస్తుంది
in
సార్.
case of A to C, there is no complete recovery and nothing is there. So that is why A to C is also not a perfectly elastic material. So this is an example of a perfectly elastic material. Okay. Now we go to another point. That is strain versus time diagram. Something called as strain versus time diagram. Strain versus time diagram. If I draw a strain versus time diagram, epsilon time. If my diagram is something like this, okay. Now this is loading. This curve is loading, and this part is complete recovery. Okay, complete recovery. Zero. This is T1. This is, let's say, T. Okay. So from zero to O dash. Let's say this point is O dash, and the strain over here was epsilon 1. Okay. Now you see over here, T2 is the recovery time. This part. This is the T2. Let's say this is the T2. T2 is from here. T minus T. This is recovery time T2. And loading happened for a time of T1. The total time taken is T. Total time they have taken is T. Okay. Now for a, if you want, if I ask you what should you change over here, what should be a criteria that this train diagram becomes a diagram for perfectly elastic material? I'll tell you in Hindi. अगर मुझे इस डायग्राम में कुछ चेंजेस करने हैं तो मैं ऐसा क्या करूंगा जिससे ये डायग्राम परफेक्टली इलास्टिक मटेरियल को रिप्रेजेंट करे? टेल मी गाइस. Any luck? Oh yeah, no. See, you have a recovery time. Perfectly elastic says that you should there should not be a recovery time also. Alright, it should be instantaneous. So for a perfectly elastic material, your T2 should be equal to 0. Yes or no?
Yes,
Yes or
sir.
no? Your entire material should recover. जैसी load remove हुआ at that very instant, it should recover back in the same direction. No, sorry, strain should be 0. No, so yeah, time should go 0. Yes or no?
Yes, sir.
So this
Yes.
should be 0. So for a perfectly elastic material, strain versus time curve will look like this. Okay, now you see what
Yes.
is this. Alright, so now today I won't take much of your time. Alright, for today we did a few things which you can revise after this. I'll tell you what all things that can be done in the later stage of time. Okay, next in the next session we will do something called as elastic, anelastic or delayed elastic material. Anelastic or delayed elastic material. It's a part of Hooke's law and this is very small part. I'll explain you something. Then we will study elastoplastic behavior. Then we will study strain energy. After strain energy, we are going to study about axial loading. Axial loading. Axial loading, which will I'll just revise you about something tapered loading, and then we are going to go to the good part, which is your bending of beams. Bending of beams. Okay. Today, anyone has any doubts?
No, sir.
Okay. Perfect.